like it.
So remember that today is the last day before spring break.
So we should just eat early.
Well, you can eat early if you want to. I don't care. And then if you missed the quiz, well, then you get an F, so that's probably good too. So in other words, this is not high school anymore. It is your responsibility and to be accountable for what you do in this class. So yeah, whatever you want to do is fine with me. So tomorrow's no class. Next week is spring break, and I'll see after today. I'll see you guys the following Tuesday. Okay, so today we'll talk about solubility. So in Chem1A, we found that some ionic compounds are soluble in water, other ones are not soluble in water. And we looked at these solubility rules, table 4.2 on page 95, to identify compounds which are soluble and compounds which are insoluble. What chemical force determines the solubility of ionic compounds in water? Jeff?
Hydration forces lattice.
Yeah, so it's hydration energy versus lattice energy. So again, that's for ionic compounds. For molecular compounds, what chemical force determines solubility? So all the way back during the first week in class, we talked about. Yep, thanks, Alex. Yeah, so dynamic forces. Now it turns out that these insoluble compounds in table 4.2 are actually very slightly soluble in water. And we can represent and quantify the solubilities of these insoluble compounds by looking at what's called solubility equilibria. So if we have an ionic compound, we're represented by AB. That dissociates into A plus aqueous and B minus aqueous. In other words, the ionic compound dissociates into its ions. The equilibrium constant is called KSP, and that's equal to A plus aqueous times B minus aqueous. And there's a table of the solubility constants in the textbook. So let's take a look at these three. So magnesium carbonate, calcium carbonate, and magnesium hydroxide are all insoluble compounds. Like we said, they're actually slightly soluble. Based on these KSP values, which one is the least soluble? And why?
Because the lowest is the lowest one.
KHP is the lowest.
Okay, so who says magnesium carbonate is the least soluble of these three? Who says that calcium carbonate is the least soluble of these three? Who says magnesium hydroxide is the least soluble of these three? Okay, good. So why is it the least soluble?
Because the factors tend to make 11 is a small number. So if you have more of the reactants below over the products, then you can have a more lower least number.
So you're saying that the KSP of those three is the largest or the smallest?
Smallest.
Yeah, so note that KSP for magnesium hydroxide is the smallest of these three compounds. That's why of these three, magnesium hydroxide is the least soluble. Okay, let's go to the next slide. So based on that solubility equilibrium, we can actually figure out what substance to add to dissolve that insoluble compound. So most carbonate salts are insoluble. We found that from the previous slide, magnesium carbonate and calcium carbonate are insoluble. What substance would you use to dissolve calcium carbonate? Write a chemical equation that represents the solubility of calcium carbonate. Explain using Le Chatelier's principle. So what substance would you use to dissolve calcium carbonate? Now, have any of you ever taken a geology course? No? Yeah, because calcium carbonate is limestone. And I took a geology course once, and the geology instructor on a field trip always had a bottle of hydrochloric acid with him. And he would put a drop or two of hydrochloric acid on rocks. And if you saw a certain observation, his conclusion was that rock is limestone. So you know what observation this geology instructor was looking for. Yeah, bubbling. And what does bubbles represent? And what is the chemical reaction that occurs which produces the gas?
Made carbonic acid became water, CO2.
Well, what are the reactants? Yes, you're right. Carbonic acid is being produced CO2 in water, but then what are the reactants which produce the CO2? Hydrochloric acid and yeah. So what these geologists do, I'm not sure if Mr. Barminski downstairs does this, but so if you have calcium carbonate, this reacts with HCl, and this is going to produce calcium chloride plus carbonic acid. But whenever you see H2CO3, you want to replace that with H2O and CO2 gas. Okay, so it's the observation of these bubbles, CO2 gas, which shows that that rock is calcium carbonate or limestone. Okay, so what equation would you use to represent the solubility of calcium carbonate? Okay, so let's go back one slide and let's take a look at this equation again. AB solid going to A plus, aqueous plus B minus aqueous. So let's apply this equation to calcium carbonate. So if we have calcium carbonate, according to this solubility equilibria, the calcium carbonate dissociates into so dissociates into calcium ion and
CO3 minus
2. CO3 what?
minus 2.
Okay, so that's our equation we can use for solubility equilibria. Now, what substance can you add to dissolve calcium carbonate? Okay, so we have that right there. So you can use hydrochloric acid to dissolve the insoluble limestone. Now, using this equation there, how can we use that equation to explain the solubility of calcium carbonate in acid? Okay, so if we add acid, are we adding reactant or product or removing reactant or product?
Removing the CO3.
Okay, so again, if you add HCl, are you adding reactant or product or removing reactant or product?
Moving the product.
Okay, so what's happening there? Okay, so for HCl, you add HCl, so what's happening? Okay, so George is saying it's removing product, so what product is being removed? And how is CO3 minus being removed? Yeah, so note that carbonate is a base, so we know that this reacts with H plus. So note that by adding H plus, that's going to react with the CO3 2 minus, effectively removing the carbonate, and if the carbonate is being removed, in which direction does the reaction shift? It's with the product side. Okay, so that's how we can explain how adding acid dissolves the calcium carbonate. Let's go into part B. Most hydroxide salts are insoluble in water. Write what substance would you add to dissolve magnesium hydroxide? Write a balanced chemical equation that represents solubility of magnesium hydroxide. Explain using Le Chatelier's principle. So for part B, I'd like you to spend a minute or two writing in your notes the answer to those questions in part B. Okay, so we can answer question B in one of two ways. So in the first way, we can draw or write an equation which represents the solubility equilibrium just like we did here. So would someone like to come to the chalkboard and write the equation for magnesium hydroxide on the chalkboard? Now you're not writing the equation. You're writing the equation for this one.
Oh, for which one?
So I'm asking you to write the equation for the solubility of magnesium hydroxide in water.
Eat that one.
So, what do you think of Bruce's equation? That's the correct. You have 2 MgOH2 going to Mg2 plus. Is that equation balanced?
Oh, you're right. He meant to. Nice. There you go.
So what substance would you add to dissolve magnesium hydroxide? So what substance would you add? What would you add? What would you add? Okay, so what does hydrochloric acid do? Yes, that's the source of H+. So based on that second equation, are you adding or removing reactant or product? Okay, so what's happening there when you add H+? Yeah, so again, just like in that previous example, I add the H+, the H+ reacts with the OH-, and that effectively removes product, and that shifts the direction of the reaction toward the product side. Okay, then the other way you can write that reaction is, again, this is what Bruce started writing. You have MgOH2. This reacts with HCl, and what are the products of this reaction?
Magnesium chloride.
Okay, what's the chemical formula of magnesium chloride?
MgCl2.
And what's the other product? Are these two equations balanced?
No.
So what do we need to do to balance these two chemical equations? We need two HCl's for which one? This one?